13ers consists of our lead and artist, Lewis Lee, our producer, Andy Fong. Then we have our programmers consisting of Jody Duff, Peter Schultz, Lloyd Scott, Lewis Stewart, and finally we have our designer, James Boa.
The aim of Revolver was to build a machine learning agent that is placed into the game in place of a real player. There are multiple reasons why this can be useful, including figuring out when the game gets unreasonably difficult for real players to help the designers figure out how difficult the game is. Another purpose of creating this machine learning agent would be to find potential bugs in the game. The agent can easily find bugs and exploits that a designer or developer could not foresee. The game uses endless waves, each increasing in difficulty, a way to test the limits of artificial intelligence efficiently. Tanks spawn from 4 different entries on each side of the square map. Each entry is blocked from the view of the center by a long line of crates to protect enemies in the first seconds of spawning. In the center is a safe zone for the player, designed to provide cover and stable gameplay. Used as walls, crates placed all around the map allow the AI to use different approaches and pathfinders to get to the enemies faster. Additionally, the main player is warned when an enemy is spawned by being alerted by a flashing light and opening door. Overall, the level is designed to provide good spectator view over what an artificial intelligence can accomplish when faced by different challenges. Keeping the map simple assured us that the AI would not find too many bugs to get his rewards faster by running in between laggy crates, etc.
In the tank's basic demonstration, you can see the trained agent seeking out the target cubes to shoot at, utilising both body and gun rotation to aim. The agent was first trained against these cubes before being trained against enemy tanks, in order to allow the agent to gain a foothold in shooting at targets. The agent here was trained for about 20 minutes and was not finalised at this stage. In the 2 other examples, the trained agent is visible in action against enemy tanks. This is the final model I developed, and it can be seen that the agent is very proficient at dispatching the targets. The agent demonstrates dodging enemy bullets, as well as shooting them mid-flight. The agent here was trained for around 80 minutes. Without first training the agent against the cubes seen earlier, the agent would likely take much longer to achieve this level of competence. The reinforcement learning ML agents for Revolver, we learned many things. First, we'll go through the pros. It was found that the agent could be used to find any gaps in the map geometry that the agent could exploit to escape the area. It could also be used to balance the game. The speed of enemy tank bullets was reduced after it was found that it was nearly impossible for the agent to dodge them at their original speed. Likewise, after a trained agent demonstrated the tactic of staying still at the centre of the map and rotating in circles, it was determined that there was not enough cover in the environment to obscure sightlines. The cons of training were that it took a lot of training and fine-tuning to produce an agent which is adept at dispatching enemy tanks. This consumed a lot of time. Additionally, with the agent being used in place of the player in the final prototype, the produced build is not interactable, but it does demonstrate RL agents sufficiently. One of the main things we learned from this was that we should immediately focus on developing a curriculum, not wasting time trying to train without one. Furthermore, the programming team should have constant contact with the designers to create an environment suitable for training. When development on the agent first began, the area created for the game was unsuitable for training due to its size and complexity, so a new area needed to be created, costing valuable time. Seekers and Planes prototypes were made with the main goal of exploring Unity's ML Agent software development kit. The end goal was to create a document that would serve as a crash course for using ML agents, ultimately speeding up development time by quickly familiarizing the programming team with ML agents and how to implement them. The Planes prototype was created to gain an understanding into how to develop agents using the Unity ML Agents SDK, and as such, documentation and tutorials were created on the group website for all programmers to refer to. Additionally, we gathered that training agents for simple games would not take long, as after 15 minutes the agent was adept at traversing the environment, and once the 15-minute mark was reached, the agent was so proficient as to never make a mistake. Therefore, training could be edited and iterated upon easily, allowing for the results of multiple training sessions to be compared in quick succession. The Seekers prototype was developed to see how the ML agents would react to players and changing environments. Within the game, the red cube roams and attempts to find the blue player target. Once it has found the player, it moves towards them, attempting to collide. If the red cube loses sight of the player target, it resumes searching. This is useful as the roaming behaviour is also utilised by the reinforcement learning tank agent in Revolver, allowing for progress to be made on Revolver whilst continuing to deepen the programmer's understanding of ML agents. The pros and cons of developing this behaviour would be that the AI produced from training is unpredictable, providing human-like behaviour, allowing for interesting and fun gameplay. However, defining the agent's observations, reward signal, and curriculum was tricky and required several iterations to achieve satisfactory results. Likewise, whilst this prototype diverted time and energy away from Revolver, the payoff was allowing the programmers to become familiar with reinforcement learning, a skill vital to further development tasks.
Pong was created as an example that the complexity of a given AI does not always necessarily correspond to how beneficial it is at performing a given task. The use of advanced AI techniques such as those classed as machine learning can cause delays in production. If a simpler AI technique can be implemented and produces the same, similar, or perhaps even better results, then this can allow the overall project to be completed more efficiently. Role-based systems are often used to give AIs different characteristics or personalities. As shown in the GIF, the right paddle constantly moves to the new position of the ball, while the left paddle, using a more complex role-based system, will predict the outcome. That is, it will predict the position that the ball will end up at when it reaches the left-hand side of the screen. Using this information, it will move to this new position, therefore giving it much greater advantage over the right paddle. The pros of this is that it's quick, easy, and doesn't require training. Once the code is finished, the AI is completed and does not need to be trained or reworked to fit into new environments. Both the role-based systems used in the Pong example are efficient and complete their objective well enough to beat a real player. The cons are that the AI produced is not human-like. It cannot improve and is very predictable. Any possible extra behaviors must be coded in. Another minigame that was created to explore AI implementation was a car game. The idea of this game was to have a car controlled by AI which would be able to learn and therefore drive around any track. This was done through another type of machine learning known as a neural network, which was trained via a genetic algorithm. This network takes in 3 inputs, being the distance the car is away from a wall, and using this information, and one hidden layer consisting of 7 neurons, it will produce 2 outputs: how much should it turn, and the speed it should move at, as well as the direction of both. This type of AI implementation had a steeper learning curve than the rule-based system used in Pong. However, after implementation was complete, the training was fast, taking on average just 6 generations of 85 cars before the AI was able to successfully complete the test track. This same neural network could also be reused into a multitude of different scenarios by changing a few simple variables, instead of having to recode a new AI from scratch, therefore making this type of AI very practical. Neural networks are good at producing more believable player behaviors, as the AI will constantly try new techniques, therefore allowing its tactics to constantly change and evolve in real time. The downside to neural networks is that they can be very computationally expensive, so therefore it's best that they're not overused when they're not required. The Doodle Jump clone was created to test how AI implementation affects the workflow when used in a 2D environment. It was also used to explore whether, given enough time, an AI would learn to differentiate between the different platforms within the game, utilizing those which are helpful, such as Double Jump, and avoid those which are not, like the breakable platforms. Although the implementation of this AI was not completed within the allocated time, it helped us learn that it can be tricky to create AI that has limited knowledge of its surrounding environment, as giving them access to this information, such as which platforms are good and bad, would defeat the purpose of training them in the first place.
Reinforcement learning is an area of machine learning where an agent interacts with an environment by following a given policy. Based on the policy, the agent will receive a reward for its actions, positive for a desired action, and negative for an undesired action. Given infinite time, the agent will find the most optimal response that maximizes the reward it receives. This is a great method in game environments where opportunities for rewards are plenty, but unviable for ones where rewards are sparse, for example if you can only reward a win or a loss. In cases like this, the agent will have trouble finding an optimal course of action to win, increasing training time significantly. In those environments, imitation learning is much more suitable. By providing a demonstration from one or more people or teachers, the agent can adopt a policy that assumes that the teacher played in an optimal way to win. Then, during the training, the agent will optimize that strategy, similarly to reinforcement learning, but in a much more believable, human-like way. A great example of this is given by Unity's ML Agents environments. In their example called PushBlock, the agent is required to push a block in a square arena onto a green rectangle floor to win. By using reinforcement learning, the agent spends a long time going in random directions and getting fooled into thinking it needs to just go onto the green floor after accidentally pushing the block onto it. With imitation learning, an example is given to the agent that the key to winning lies within pushing the block, as the teacher would do so in every attempt. This showed a great difference in training as the agent explored the idea of pushing the block earlier and much more often, until it eventually beat the human player. Considering the rapid pace at which the games industry is moving forward, it is crucial to find ways to improve the speed and efficiency of various development stages. That's where machine learning comes in. One of the most time-consuming areas of development is definitely map design and creation. Being able to speed up or simplify this process would allow more time to be put into other aspects of a project. Machine learning can be used to speed up map creation. Training agents, however, can take a long time and require planning. To remedy this, a pre-trained engine could be created instead that developers would be able to use and adapt to their specific application. Basic training with supervision would be done in advance, providing machine learning agents with a certain number of assets, each asset with an assigned worth. The agent will then start placing the assets until it runs out of credits, and a supervisor would rate each map to slowly better the results. As a result, the agent would start to learn patterns that are considered good by humans, and adapt its placement to create good maps more and more consistently. This, of course, would be an excruciatingly long process when using reinforcement learning. That's where imitation learning comes in. Before the training, designers can provide quality maps with varying layouts as an initial dataset for the agent to speed up the training. Avoiding hard-coded layouts reduces perceptible repetition, and not using random number generators allows for more believable maps.
Player disconnects are a huge issue in competitive and online co-op and multiplayer games. This creates large disadvantages for the team with the disconnected player or players. We may be able to alleviate this issue by using machine learning to build a neural network of the player's playstyle and movements over hundreds of games. When the player disconnects or is having connection issues, the neural network can step in for the player, mimicking the player's playstyle and therefore softening the blow on the allied team. In the planning stage of the creation of a game with the use of reinforcement learning or imitation learning, the game development process is quite similar to a regular planning stage. However, there are a few factors which will influence this stage. As these technologies are fairly new and being updated every day, accounting for time needed to learn new machine learning technologies is vital. Also, huge spans of time where training will occur will have to be taken into account. When pitching the game to investors, sufficient argumentation would have to be provided regarding the benefits of using machine learning as opposed to the conventional, established, traditional artificial intelligence. Why invest in training and implementing machine learning techniques when traditional AI could be good enough and less likely to disrupt development? This is something that needs to be explained to investors in a way that someone not experienced with machine learning development can understand. During the production stages of the project, assuming the team has a plan for implementing the machine learning into the application, it is important to use team management software and development or communication tools to ensure tasks are getting completed on time. As the software is written, documentation needs to be written to ensure communications between developers and operations are maintained. This will ensure that time for machine learning is included as part of the time plan or the Gantt chart. During the testing stages of development, the use of machine learning can speed up or even entirely replace teams of game testers. This is because when using machine learning agents to test various aspects of the game, the agents can find obscure and unthinkable ways to break the game in order to receive rewards. This, however, may be an unnecessary waste of time, so during the testing stage, it needs to be decided whether or not machine learning will be used for testing.
Machine learning is crucial for developing adaptive systems and environments. It could help provide a fresh experience for players every time they start a new game, taking away the need to hard-code custom changes based on players' doing, and creating essentially limitless possibilities for how the game can progress and end. Generating random behavior in games can come with many problems, as random number generators are never truly random, relying on some form of seed and often creating repetitiveness and other times potentially unwanted behavior. Accounting for those issues is problematic and time-consuming. Imitation learning could be used to steer the randomness towards a more desired behavior, for example in random map generation. There is nothing that ruins immersion more than stuttering, lag, or inconsistent quality. Machine learning has already been utilized in the past to improve different aspects of games, like textures and shading, from upscaling the textures without noticeable imperfections, to dynamically adjusting the quality of areas that the player is unlikely to be focusing on. It could also be used, for example, to learn from a player's behavior what areas or assets to preload, to save on memory and processing power where it matters.
With the amount of time spent going back and forth between artists and developers when creating assets for production, it would be ideal to minimize this time and complications between communications. This could be done with the aid of AI by training an agent to sample drawings and create a UV map to be imported into a modeling software. The AI would also be able to sample colors used within any drawings to create a texture map to be imported with the UV map, effectively creating a full 3D model from a 2D drawing. To teach a potential machine learning agent how to turn 2D artist sketches and assets into 3D models, you could use a labeled dataset containing previous examples of 2D artist sketches or textures and maps alongside the completed model. Being able to very quickly produce rough models would save a lot of time when prototyping and throwing ideas of what the final product could be.